Hello, everyone. Um, Welcome back. Today is day 93. Today is a bit not so. I don't know. Today did not go as expected. I am late to the stream. It's been a rough day. Um, but I still managed to make it back to the stream, which is really good. Better late than never, right? That's what they say. Anyways, it's good to be here today, and oh, I don't know. I think I should notify my. Anyways, there is no need for that. But if you're watching this now, I think it's either you're, watching this late in the night, meaning you're study late in the night, or you're just Let me remove this part. I don't know why they do that. You're just maybe our time is different, right? But in either case, I really appreciate you being here today. Thank you guys for coming through. Every time I make this stream, uh, it's just really awesome. Yeah, I know it's late. I know, right? But yeah, I'm just getting back home now. Since morning I've not been around, and yeah. How are you, Ransom? Okay, so let's let's take a look. Let's take a look. Hello, Comfort. What can we do today? I know it's very late. It's very late now. I think it's like 10 p.m. Yeah. Oh, okay. We are going to learn about sorting algorithms. At least that's what I plan to do today. But with the way the day went, I don't think I'll cover much. But we'll just use the remaining time to see what sorting algorithm is and the different things we can learn about sorting algorithms. All right, so let's take a look. I linked this resource in the description below, so in case you want to read what I'm reading, um, you can learn about it. How do you know I'm standing? Well, I'm actually standing because I have a standing table and I don't want to sit down. Yeah. Okay. All right. So, yeah, we'll get started. We'll learn about sorting algorithms. Okay, so you can read about sorting algorithms. I left a link in the description below. And yeah, so a sorting algorithm is used to rearrange a given array or list of elements according to a comparison operator on the element. Okay, so a sorting algorithm is used to rearrange items in an array, right? Based on the way you want to arrange them, you can arrange in non increasing order and non decreasing order. So, yeah, those are like the reasons why you want to use sorting, but let's continue reading to see more about it. So, for example, the below list of characters is sorted in increasing order of their ASCII value. This that is the character with lesser ASCII value will be placed first than the character with a higher ASCII value. Okay, so we have what is sorting. So this is an image of an unsorted data, and the desorted version is on this side. Okay, so what is this? What do we have here? This. Oh, okay, that is strange. Okay, so let's continue. Um, we have what is sorting, right? Sorting refers to the rearrangement of a given array or list of elements according to a comparison operator on the element. The comparison operator is used to decide the new order of the element in the respective data structure. Sorting means reordering of all elements either in ascending or descending order. So, like I said, ascending means increasing order or non decreasing order, and descending is from higher to low. So, non increasing order or decreasing order. Anyways, let's continue. Sorting technology, in place sorting. So we have different types of sorting, at least the different ways to sort, right? Not the types necessarily. So we have in place sorting. An in place sorting algorithm uses constant space for producing the output, modifies the given array only. It sorts the list only by modifying the order of elements within the list. Example is selection sort, bubble sort, and insertion sort and heap sort. Now I don't know about these types of sorting, but we'll learn about them as we keep reading. At least we'll learn about selection sort for now, which is the first sorting algorithm we have on our list. Okay, so we have internal sorting, right? Internal sorting is when all the data is placed in the main memory or internal memory. In internal sorting, the problem cannot take the input beyond its size. Example is heap sort or bubble sort or selection sort, quick sort, and so on. Yeah, I'm not going to read everything now. So let's go to the more interesting part of this article. And by the way, I have this article linked to the description below, so in case you want to read the same thing, it's already there. Now, characteristics of sorting algorithms. So we have time complexity, obviously. So the time complexity is a measure of how long it takes to run an algorithm. Now, I think time complexity is most of the cases you find a definition that does not really mean the same thing as the actual definition of time complexity. Time complexity is not really how long your code took to execute, right? It just means the time. It just means the different um, the different steps, right? It takes to complete that code. If we're to measure time complexity in terms of the time it takes to execute a certain code, then that will not be fair because some programming languages are faster than the others, right? So, meaning it will really be based on a lot of factors rather than the actual performance of the code itself and not the time it takes to process everything. So, if, for example, if you say running a mile, right, is just like if you run in a straight line, right, it takes you a certain time to run that mile, right? But if there were a lot of, let's say hurdles on the road before you get to the end of your journey, right, it takes you less time to complete the race this time around. But if we're to say, okay, now if we're to compare the speed based on how much the person weighs or what they are putting on their clothes, then that's a different thing, right? It's not really about the road itself this time around. It's just now the road and the person that is taking the journey. So time complexity really is not well explained in most cases, but anyways, it takes time to actually understand what time complexity really is. So it's not really about the code, the time it takes to finish the program. It's actually how many steps, right, your code takes to complete. Okay, so let's continue. So now time complexity really plays a factor in the sorting algorithm. And so we have time complexity. Yes, time complexity. And this is a measure of how long it takes to run an algorithm. and is used to categorize sorting algorithms. So the worst case, average case, and best case performance. So big O notation, right? Big O is simply um worst case scenario, right? How badly can your code perform, right? How long will it take your program to actually complete? Okay, so now let's continue. We have space complexity, yes. So in this case, where we explained, I think in place sorting, right? In place sorting means we are sorting the algorithm in the same input, which is a list or an array, if you will. And yeah, so that also is part of the characteristics of a sorting algorithm. So the space complexity as well. Now we have stability. What is stability? A sorting algorithm is said to be stable if the relative order of equal elements is preserved after sorting. Okay. This is important in certain applications where the original order of elements of equal elements must be maintained. Okay, so let's, to my understanding, right? Let me read this again. A sort, so we have stability as part of the characteristics of sorting algorithms. So a sorting algorithm is said to be stable if the relative order of equal elements is preserved after sorting. So let's say, for example, right? I'll erase this board now, and we'll take an example to see. Yes, confirm. Clear the whole canvas. Where is my? Just give me a second. I need to find my. Okay, I don't know where I dropped my. Okay, I found it. So I was looking for my pen to write. So the stability, right? Let's say, for example, we are given an input like this. We are given an array to sort. So and our array is like this. So let's take here. Okay, that's really huge. Let's reduce this. Okay, 20 is too small. All right, so we have an input array in this form. So we have, let's see, 3, 2, 5, 2 again, and 7, right? And we are asked to sort this array, right? So what we expect to have, and what this stability really means, is a sorting algorithm is said to be stable if the relative order of equal elements is preserved after sorting, right? This is important in certain applications where the original order of equal elements must be maintained. So equal elements in this case is 2 and 2. So meaning when we sort this array, right, we should have something like this, 2 and 2, right? We should maintain the stability. The amount of equal numbers should also be maintained in the sorted form. So we have 2 and 2, then we'll have 3, 5, and then 7, right? So meaning the input is still stable, right? We still have both equal elements present in the sorted version of this array. So that is what I understood by that. So let's continue with the next part. So we have here in place sorting. And in place sorting is the one that does not require additional memory to sort the data. This is important when the available memory is limited or when the data cannot be moved. So, for example, when we know when we create an array, right, it creates more space in memory. So, meaning this consumes memory in our system. So what we need to do is to sort the array in place. So we do not need to create an additional array like I did here, right? To sort this array, right? We need to do it in place. We need to sort the array in the same, or we need to sort the list of integers in the same list, right? So meaning the sorting should have happened here. So we would have had 2, 2 and 3, 5 and 7, right? The sorting should be done in place and not when we create a different input list. All right. So that's about it. Let's look into more practical stuff. So applications of sorting algorithm, we have it in the searching algorithm, right? Searching is often a crucial step sorting is often a crucial step in searching algorithm like binary search. Yes. So in order for us to perform binary search, you remember very well we need to sort the array, right? So let's quickly make a binary search example. So let's say we are given a list of numbers. So we'll have 3, 5, 6. I'll just put, okay, this is already sorted. Let's put 6, 8, 7, 9 and 3, right? And let's say we're looking for, okay, let me put like a, okay, yeah, 3 is okay. So let's say we are looking for 8, or there's 7 in this array, right? Or in this list. I keep saying array, but let's use list for now. So we are looking for 7. 7 is our target. Now, in order for us to use a binary search, we need to use 2 pointers and constantly divide the array and constantly divide the lists of integers and search each half to see whether our our target is within that half, right? And the good thing about the binary search, is that there is a chance, right, that we are likely to see it in the half we just found. So, meaning if we're looking for 7, right, all we needed to do is to divide this array into 2, to divide this list into 2. I might use arrays sometimes. I'm just used to using arrays, but let's continue. So we'll divide this into 2, and then we know our target is in this half, right? So automatically we eliminate the need for searching through the entire list, right? Normally our brute force solution would have been to go through the entire list until we find our target, right? Meaning we'll have to go from this point, then we move to this side, then we move to this side, and we find our target at this point, which takes O of n time, right? At least for now. But with a binary search, right, the search is halved, right? We don't need to go through the entire array, through the entire list to find our targets. And for us to perform a binary search, we need 2 things. We need a pair of pointers, right? We need a pointer at the left and at the very end, which is the right pointer. Now, the reason why we use these pointers is because we know the pointers will appear in the array at a position where the array has the smallest element at the beginning and the larger element at the end. So, in order for us to do that, it means we need to be sure that we have our smaller element at the beginning of the list, or the array in this case, at the beginning, and the larger one at the end. But how are we sure that we are always going to have the beginning and the smallest element at the beginning of the list and the larger element at the end? Well, one way we can do that is to ensure that the list is actually sorted. So we need to sort the list. So in this case, we'll have to run the sort function on this, right? So we'll do 6. After sorting this, we'll have 3 at the beginning, 6, then 8, then 7, 8, and 9. Right now, our list is sorted. So this will be valid for us to tell our pointers that, okay, the left pointer, you are at the smallest element, and the right pointer, you are the largest element. So with this, we can then begin the binary search, and the binary search is done in this way. So we find the midpoint of this list, which is going to be the position of the left pointer plus the right pointer divided by 2, and we round that value to the nearest 0 value. So this is going to be at index 0. This will be 1, 2, 3, 4. So this at index 4. So this will be 2, sorry, 4 plus 0, which divide by 2, which is 2, right? So 2 will be our midpoint. So the value at the midpoint will determine where we should search for our target. But in this case, 2 is already at the target value, so we found our target. And you can see this is better than just iterating through the list and looking at every element in the list in order for us to find our target, right? So that's one thing that is really good with binary search. And for binary search to really happen, we need a sorted form of our input. Our input has to be sorted, and that is where we are heading at this point. So we need a sorted array or a sorted list to be able to perform binary search, right? Which is one of the applications of the sorting algorithm. And there are many more: database optimization, data management, machine learning, data analysis, operating systems, and so on. So you can read this and understand how they actually work. So basis of sorting algorithm. So we have some sorting algorithm applications here, but we're not going to go over all of this for now, right? You can read this on your own, which is a really good read. I think this Gigs for Geeks is one of the best platforms or best resources to learn anything programming related. So you should check it out. I linked the link. I left the link in the description of this video, so you can have a look at it. Now we have a lot different types of sorting algorithms. We have selection sort, we have bubble sort, insertion sort, merge sort, quick sort, heap sort, counting sort, radius sort, and so on. Oh my god, this is a lot. Anyways, I don't think we can learn all of this in a night. Even becoming good at one, in fact, will take you quite some times, right? So let's see in the chat whether there are any questions. Let me refresh this. Yeah, I said my window. Okay, he said Bogo sort is the best. Oh, okay. There's Bogo sort or permutation sort. I can see it right here. It just right in my face. Okay, that's it for now. Let's let's um let's learn about selection sort. I think selection sort is the easiest among all of them. So let's carry on and see how selection sort works. So selection sort is simple and efficient sorting. It's a simple and efficient sorting algorithm that works by repeatedly selecting the smallest element or the largest element from the unsorted portion of the list and moving it to the sorted portion of the list. Okay, so let's continue reading. The algorithm repeatedly selects the smallest or largest element from the unsorted portion of the list and swaps it with the first element of this unsorted part. This process is repeated for the remaining unsorted portion until the entire list is sorted. Okay. Oh, I remember I wrote code for selection sort algorithms. Okay, that's nice. That's nice. Um. All right. So, how does selection sort algorithm work? Okay. So let's consider the following array as an example. So, come on, stop. So we have an array of 6, 4, I mean 64, 25, 12, and 22. So here is an unsorted array. So let's see how the sorting would work. So for the first position in the sorted array, the whole array is traversed from index 0 to 4 sequentially. I think this is the unsorted array, right? Anyway, the first position where 64 is stored. So for the first position where 64 is stored presently, after traversing the whole array, it is clear that 11 is the lowest value. Okay, thus replace 64 with 11. After one iteration, 11 which after one iteration, 11 which happens to be the least value in the array tends to appear in the first position of the sorted list. Okay, so meaning we have to traverse the entire list, get the least element or the smallest item or integer element in the array, and then place it at the beginning. Okay, this is good. I wonder how long that would take. The time complexity for this algorithm will be really, it's I don't know, maybe quadratic time. Let's continue. So second pass. So second pass means second iteration. So we iterate again for the second position where 25 is present, right? So we find 25. So we move past this pass. So this is the sorted portion at this point. Okay. Again, traverse the rest of the array in a sequential manner. So we need to traverse up until the end, right? And then determine which one is the lesser one and replace it at that position. Okay, this makes sense. So after traversing, we found that 12 is the second lowest value in the array, and it should appear at the second place in the array. Thus we swap these values. So we swap 12 with 25. Now we don't swap 12 with 25 because we made 12 here, right? We swapped it because as we traverse the remaining portion of the array, 12 was the least value we found so far. So we swap it with this one. Okay, so let's see this part. We do this for the third pass and so on. So these are just the explanation. And here is a Python code for the sorting algorithm, right? So we start with range, the length of the length. Why? Okay, so we have to stop here because we want to return, swap the values. Okay, this makes sense. So for J, so this is minimum index, right? So we find the minimum. So the first value we chose, right? In this case, for the first iteration, this will be our minimum. 64 is our minimum, right? And then we use a second iteration. Okay, so this is going to be O of n squared, quadratic time complexity. And then we use this to traverse the remaining array, right? So we'll go from here. So this will be so we'll start one after the initial point, okay, and then we find out if the current value in this iteration is less than the value we found before, right, which is the minimum index here, right? If it is, minimum index becomes j, which is the index of the value in the current iteration, and we'll do this to swap the values, right? Okay, so let's see the time complexity analysis of selection sort. So you can see the time complexity is O of n squared. Like I said, when you have a loop within a loop, it's usually O of n squared, right? No debate about that. Okay, so advantages: it is simple and easy to understand, works well with small data sets. You know what, let's bring this here. Oh wow, I didn't commit this code yesterday. Wow, that's really bad of me. So it add, I thought I did. I sincerely thought I did yesterday. Weakest row, I think it's arrays and strings, right? It's arrays and strings. So arrays, strings. This is lead code 1337. Okay, so let's see how we can do this. So this is going to be a new folder. I'll call this sorting, but you know what, let's call this sorting right? Sorting dash algorithm, and then we create a file for the basics. So basics like this. Yes, so okay, so we have that in place. Now let's continue with the implementation. So we'll write a function to perform um, the implementation um, of a selection sort, right? So I'll just leave a comment here and call this selection. So selection sort implementation. So we need to define a function. I'll call this selection underscore sort. Okay, come on, not spot, sort. And this function needs to take in an array, right, or a list, and then sort that list. We don't need any more inputs, we just need one input, right? So we'll say I'll call this nums. Nums is going to be a list of integers. So this is going to be a list of integers, and then we need to import this. So I'll say from typing import list. Okay, so we import list from typing and so on. All right, so now we need to begin the implementation. So what we do in a selection sort is to simply change the positions of values in the list, right? So meaning we need to traverse the list from a certain point up to anywhere in the list, and then so let me use this board here. I'll remove everything here, right? And then we'll perform this. Let's visualize how the selection sort actually works. So we start our iteration, and our iteration has to run from this point all the way to, okay, I'm using the wrong tool to draw. So our iteration has to begin from this point all the way to this point. Now the reason why we have to stop at this point is because we need to swap the elements, right? We need to swap the elements, and our second iteration, our inner loop, will run from this point all the way here, right? So we need to ensure there's enough space for us to continue the iteration and swap values. Otherwise, when we get to this point with with the outer iteration, then there is no value to swap this with, right? Because the second loop will iterate up to or after this one, right? One plus this one. So in this case, it will be at an index larger than this, which is outside the list itself, and it is out of range. So we don't iterate up to this point. So we just run the loop all the way to this 9 here, right? In other words, the length of the array minus 1. So we can take it here, right? So we start our iteration here. So I'll call this I, right? So this is the first iteration. Now, for now, we know I is our current lowest value. Until we see another value, we know, I which is at the value of I is the index, which is 0, and the value or the integer at index 0 is 6. So currently 6 is our lowest value in the array. So that is what we know for now. Until we continue searching the entire array, we don't know if there is any other number that is lesser than 6. So for now, we only have 6 as our smallest value. So the next thing to do is to iterate through the array and then compare the values and see which other one is lower or smaller than I, right? Than the value at I, not I itself. So than 6 in this case. So this will be So we'll start, this will be j, right? So we'll compare the value at j with 6. So in this case, the value at j is superior to 6, so we continue. So we move j forward. We compare, it's still superior, we continue. We compare, it's still superior. Then we get to this point. Now 3 is less than 6, so we swap these. So we swap, we bring this here and we bring this here. Then our I moves from this point to this point and j goes back, right? So we see this value, right? We say, oh, okay, are these values equal? Or, you know, which one is the smallest value for now? So here, currently, 7 is smaller than 8. So we continue. So we know for now our smallest value here is currently 7. Okay, so we continue the search by increasing j. So we are at 9. 9 is still superior to 7, which is our current smaller value. Now you can see I did not move I yet. I is simply an indicator, right, of where the current smaller, the next smallest value will go into, right? So we can have a different variable that keeps track of the smallest value as we iterate through the list to find the smallest value. So j here is going to do that for us. And if we see a smaller value, we update that value, which is going to be in an array. Which is going to be a different variable, right? As you can see here, right, the implementation shows that. Let's just look at this, right? You can see main index keeps track of the current value. Now you can see we are not, sorry, mean index is here, right? As you can see, we are not changing I, right? I is just an indication that this is where the swap of the next value will go into, right? So in this case, we'll need to keep incrementing j until we see a value that is less than the smallest value we've seen so far. Now in this case, it will be 6, right? So we swap 6 with 8. So we take 6 out and we replace 8 here. So now you can see our sorting is beginning to take shape. And after the swap, right, we move the pointers, we adjust them back again. So this will come back to this point. Now 7 is the current smallest value we've seen so far, right? Then we'll continue searching 7, 9. So we don't have any smaller value here. There's no swap happening. So we continue again, we get to this point, right? And yeah, so at this point we have I, right? And it's the value at this position is 9 and our j is here, right? Now this will be the last iteration that will happen in this case, right? Both in the outer loop and in the inner loop. So we have j which is at position 8 and 9 is here. So we swap the values here as well. So we'll swap 9 with 8 because 9 is superior to 8, right? And we do it this way. So we take this and that. And yeah, so with this, we sorted the array using a selection sort, right? Selection sort algorithm. And we did the sorting in place, so there is no creation. There was no creation of extra array, which will obviously cost us extra memory. And the time complexity for this to happen was O of n squared. All right, so yeah, I think that's all I actually planned to do today. I did not want to miss today's date. So anyway, so let's implement this quickly here. We are simply rewriting the code we saw on Geeks of Geeks, but we just want to see it in action, right? We'll test out things and how it actually works. So we'll say here we'll say we need the length of the array, so I'll call this n is going to be the length of nums like this, okay? And then we'll say so we want to iterate, right? So we'll say for I in range of n minus 1, right? We'll call this current mean, which is current minimum, and set this to be equal to I, right? So the first value we see is our current minimum, and then we'll do this. So say we'll use an inner loop, right, to find out the next minimum possible, and then we'll update the value of the current mean here. So we'll say for j in range, now j will start 1 plus I, right? 1 after I, so which is going to be I plus 1, and then it will iterate up to n, right? The last item in the array. Okay. Now the next thing to do is the comparison, right? Whether the current value at j, which is the current index in the second iteration or in the inner loop, is superior to our previous current value. So our previous current value would be, the nums at I, right? Current mean, right? So if this number here is superior to the number at j, so which is going to be nums at j, right? Then current minimum becomes the new current here, which is going to be equal to nums at nums at j, not the nums at j per se. We want to replace it with the current index, so this is going to be j, right? And at the end of the iterations, right, we need to swap the values. So we'll take nums at this current num, right, and then we'll swap it with the next value. So we'll say nums at I will no longer be nums at I, right? Nums at I, and then nums, so the value we just found, right, which is our current minimum, we'll swap it with the old value that was there, right? So num at current mean, right, will be equal to nums at current mean, and then nums at I, right? So now the swap has been done, and then all we need to do is to return nums like this. Okay, so let's just indicate that this is going to return a list of integers. Okay, so all right, so let's test this out and see. So I'll say print selection sort, right, and pass it this value. We'll pass it 66 800 130, right? And let's see what this will give us. Now you can see we have 0 3, and then now you can see we have a bug. 3 came before 1, and I don't know why. So I mean the rest is properly sorted, but why is there 3 before 1? Inside life. Hello Yash, thank you very much. Thank you. Nice to have you here. Okay, so let's see what might have gone wrong. So we have yeah, I mean, what could be the issue, right? Since when is 1 superior to 3? You know what? Let's test this in their own environment and see what's wrong. I mean, the concept is here. Everything was done properly, so I'm not sure what went wrong. Oh, come on. Let me copy it first. Okay, so let's see. Dun 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 dun. Dun, 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 dun. Can I test this out? I don't think I can. Okay. Oh, come on. Sort of. What could be the reason why? Is there any reason why 1 should appear after 3? I mean, 1 is never going to be superior to 3. So if the current minimum is superior to number at j, then replace it. And the replacement was done here. This is very interesting. Current min. Well, this shouldn't be happening at all. Is 1 being regarded as a huge number? I don't get it. So let's say this was 12. Right? The sorting is done properly. Is there an issue with 1? I mean, I'll find out that, but this is really interesting. This is very interesting. Okay, I think I'll just close up for the day and we continue tomorrow. Hopefully, I come early tomorrow and stream so that we have more exercise to do, right? So, git add, git commits -m. This is sorting algorithm, and we'll just put basics here. Basics. Is git push origin main. Origin main. Alright, so yeah, I think that's it for now. And we shall see tomorrow. Thank you guys for staying through. Good night, everybody. Good night, Ransom. Good night, Comfort. Good night, Yash. And tomorrow is another day to write some awesome code. And I'll see you guys tomorrow. For tomorrow is an exciting day. Will be an